So chemical reactions. Physical changes versus chemical changes. Physical changes occur when the appearance of a substance changes, but that chemically the substance is the same. Individual molecules do not change. If it said H2O at the beginning, it should still say H2O at the end. Okay. Examples of physical changes are melting, freezing, and or changing of size or shape. Okay? So all your change of states are all physical changes. The formula is still the same. Water, whether it's a solid, liquid, or gas, is still H2O. Right? A physical change also occurs when substances are mixed and when something dissolves. So like when you mix salt, water, or Kool-Aid, those are all physical changes. The water, salt, and sugar keep their properties. And the substances can be separated again. Now for a chemical change occurs. I'm going to use the triangle for change. Occurs when the atoms making up matter rearrange to form a new substance with new properties. This usually occurs during a chemical reaction. RXN is a way to shorten reaction. Now notice this is not new atoms produced, atoms destroyed, molecules destroyed, compounds destroyed. It's just a rearrangement of atoms. Matter cannot be created nor destroyed. The mass cannot be created nor destroyed. It's just an entire rearrangement of atoms. That's why you have to work on balancing those equations, because when you have a balanced equation, that's what keeps all of those atoms into account. So evidence of a chemical change. We see production of gas. Well, a way to see that would be bubbles. Let's stick to pink. Bubbles. Foaming, odor, fizzing, smoke. Color change. Now, not all color changes are chemical. This is one that you have to use logic for. If I mix food coloring and water, that is not a chemical change. You just mix the two things, I can still filter out that color. However, when a leaf turns from green to brown to red, those are all chemical changes. That leaf can never go back to being a pretty green leaf. Okay, so that's a chemical change. It's a one-directional rearrangement of atoms. But this can be an indication of a chemical change, color change. This is when a new color or a unexpected color. What I mean by unexpected, that's the easiest way to keep the color changes independent. If I mix black paint and white paint, I should get gray. That's just a mixture, that's just a physical change. If I mix black paint and white paint and end up with red paint, a chemical reaction must have occurred. That's an unexpected new color. Rearrangement of atoms created new compounds that have new colors. Okay? Now, the formation of a solid or a precipitate which is a solid at the bottom of the container. If it gets cloudy or if it gets foggy, mixing two liquids and all of a sudden this thick paste falls to the bottom, that would be a precipitate. And the last one, a change in heat or light energy. So if you see sparks, if you see an explosion, if you see glowing, Temperature increases or decreases. All of these should be signs of chemical change. Being able to recognize and identify a chemical change is important. And you need to be able to support it. So you say, this was a chemical change. I say, why? You need to be able to identify this evidence, these examples that you know a chemical change has occurred. Okay. So these are only clues. A chemical change has not actually taken place unless the matter has changed into a new substance. There's going to be exceptions to all of these. Some common examples of chemical changes include rusting, tarnishing, burning, cooking, and digesting. If you have the chemical formula, well, let's talk about the total equation. If you have the chemical equation, you can tell if a chemical change has taken place by looking to see if the products in the equation are different from the reactants. Okay. Hopefully this is all review, but I've seen a lot of people struggle with just chemical versus physical. Okay. It's all going to depend on that chemical reaction, and what we're going to be talking about throughout this whole packet is chemical reactions. You can have a chemical reaction that shows a solid going to a liquid, H2O solid going to liquid, just an energy change. So it's not that it has to have a chemical reaction. That's a way to write it out and calculate energy. It has to be that the compounds that you started with are not the exact same compounds that you ended with. That is a chemical change. Now, at the bottom where we talk about equation symbols, you need to read through all of this. Okay? Identify some things here that you didn't realize. Having aqueous, solid, liquid, and gaseous, there's some very important ways to know when you should identify something as a solid, liquid, gas, or aqueous. Those are going to be those key terms. It's very important that you understand this here about weak acids versus strong acids. You should have already had those memorized. Strong acids dissociate. They break apart into their ions every time. Weak acids do not. So all acids and bases are aqueous. So anytime you're writing an acid or a base, you put the AQ beside it. It has to be aqueous. That's how we identify it as an acid or a base. It's in a solution. However, whenever we are breaking apart these ionic bonds, if it's a weak acid or a weak base, you can't break it apart. And instead of memorizing the 10s, 20s, 30s, the tons of different weak acids and bases, we just memorize the few strong acids and bases. If it's not a strong acid or a base, it is officially a weak acid or base. Okay, so if it starts with an H, think about it. Is it one of my strong acids? Nope, it's weak. If it ends in OH, is it one of my strong bases? Nope, it's weak. Okay, so make sure you identify and be able to use that. At the very bottom, here's some general considerations that you need to cover. You need to read through and always keep those in mind. Making your 7 diatomic elements, Br2, I2, N2, Cl2, H2, O2, and F2. C is not a diatomic element, and I saw that problem a lot yesterday. If it is not diatomic, you do not put a little 2 beside it. So types of written equations. The molecular equation, an ionic equation, and a net ionic equation. The molecular equation is what you're used to. Every single compound that was present when the reaction occurred is written out, and it's completely balanced. That is a molecular equation. It's big. It's difficult to work with. Full equation. An ionic equation is one where we take each of those compounds, and if they're aqueous, we break them apart into their ions, unless they're a weak acid or base. But if they're aqueous, we break them apart into their ions, and we show they're separate ions. For a net ionic equation, and that's what the rest of these notes will be over, any ion that is the same that when you started and is the same when you ended, didn't actually do anything in the chemical reaction, we get rid of them. So you end up with just this net ionic equation. We want to see a net overall. What actually did anything? If you start out with sodium chloride and you end up with sodium hydroxide, and that sodium didn't do anything, didn't make any new solids, didn't make any new substances at all, it's still just a free-floating ion, there's no reason to have it in the chemical equation. It didn't do anything. You could have replaced it with any other ion that would have done the same thing. Okay? So for writing net ionic equations, many double replacement reactions involve a reaction between two aqueous solutions. These solutions each consist of a pair of ions resulting from the dissociation of a soluble compound. So ions result from the dissociation of a soluble compound. We know soluble compounds because they start with our soluble ions or end with our soluble ions. If it starts with NaK or NH4, it is always soluble, no exceptions. If it ends in NO3, always soluble, no exceptions. So we decide each one of these compounds, if they're soluble, they break apart. Now chloride is usually soluble as well, but you wouldn't have to have its solubility rule memorized. The only rule you have to have memorized for AP chemistry anymore are those 4 ions. Okay. Sodium, potassium, ammonium, nitrate. So when 2 solutions are combined, the 4 ions in the solutions mix. As the ions move about in the solution, they collide with other ions. Okay, I put the solid in the water. It breaks apart into the ions. The ions are constantly moving. Atoms have to be moving. So they'll hit another one. New positives and new negatives will interact, which will create new compounds. So as they collide and form the new ions, or new compounds, that's how a new reaction is occurring. And if this forms a precipitate, if these ions collide with each other and the new compound it forms is not soluble, then a precipitate will fall to the bottom of the beaker. A new substance has been formed. These 2 liquids have produced a solid. That's how you know a chemical reaction occurred. So if no combination of positive and negative ions results in an insoluble compound, there is no reaction. Nothing new is produced. It's just a mixture. You mixed all these ions together. Notice that the same 4 ions are present on both sides of the arrow. If I have this soluble compound forming this, all of the ions are the same on both sides. So no reaction occurred. However, if a solid is produced, like in this case, I mix 2 aqueuses, I form a solid. I break everything that I can into its ions. So this has sodium, so it breaks apart into its ions. This has nitrate, so it breaks apart into its ions. This has both sodium and nitrate, so it definitely breaks apart into its ions. But a solid cannot break apart. Only aqueous solutions can. So when I go through my net ionic, well, I have sodium on both sides. It did nothing in this reaction. I have nitrate on both sides. It did nothing in this reaction. What actually happened in this reaction is this ion of sulfate and this ion of barium combined to make a solid. This is where the actual chemical reaction occurred. So a net ionic equation gets down to the nitty-gritty, what actually happened. We don't include anything that didn't do anything, okay? So to write the net ionic equation for the example, you'd follow below. Break apart what you can and get rid of any ions that aren't around at the end.